各位那个台大的同仁啊，大家好，前辈先辈们大家好哈。那今天我们邀请到刘立芳教授来给我们演讲。那刘老师，我相信在座各位可能都比我更熟啦。那刘老师得过美国工程院院士、ACU 的 Fellow、中研院院士。那这次他是应玉山学者回台湾一阵子，那刚好也得到今年的台大的杰出校友哈。那学术类的杰出校友，那工学院就希望说可以邀请刘老师可以跟演讲，那所以就由我们水工所来安排。那我们也联络了台大演讲网的部分，然后就会之后的演讲会放在网络上。那我开场用中文介绍哈 ，so I introduce Professor in Mandarin, but actually we have English foreign student, so I think both are fine. You can deliver it in Mandarin or English, OK. 好，那我就不耽误时间，那就把时间交给刘老师。
谢谢尤所长，是非常高兴有这机会，来台大，来跟大家谈一下我最近在新加坡跟一位就是研究生博士班研究生做的一些关于海啸的关系问题。So anyway, I think I'm allowed to present in English. That is a little better because I can speak a little faster and using the proper terminology, and you probably can understand actually better. All right, the point here, my co-author, the co-author, actually that's his main work, Ignacio, and he just recently graduated and get married and moving to UK. And in January, he is going to work for the HR Willenford, the one who makes wave makers and doing consulting work in coastal engineering. And it's a UK version of a DHI and Deltaris, so in Europe. All right, so as stated in the title, we are interested in understanding what we call a tsunami-like bore, and how do we generate it, and how do we study the evolution of the bore in the laboratory setting, and then finally looking at the more important issue, which is the inundation and the flooding in the coastal area. So just to motivate and give you some justification why we want to look at this type of problem is because during the last two significant tsunami, one is 2004, that's the Indonesia or Sumatra earthquake generated the Indian Ocean tsunami, and these are the pictures taken in Thailand, Kupu, coast of Kupu, and you can see from the picture that the signature of the leading wave of the tsunami certainly look like a very, very long crest wave with a very relatively sharp or steep slope front, and in fact they are breaking for this. And then this another particular picture taken here give you the impression that is some kind of undulating bore. In other words, you have a bore front, then followed by trail of oscillating surface. And in fact, this bore actually has a very long wavelength. The length of these bores are quite long, and which eventually cause a very long duration of flooding in the coastal region. All right. So that is the evidence. This short video we cut it. The original video was very long. That was taken during the 2011 tsunami in Japan. This is in the Bay of Kuji, showing that again the leading wave of the tsunami wave looks just like a bore, like Qiantangjiang, the bore propagating into the bore, and very, very long crest. Practically looks like one uniform long crest, and obviously breaking because you see the air bubbles generate or trailing behind the wave front. And I think the video will stop pretty soon. And then the bore length, the length of this bore actually is very, very long, extend a few kilometers long, right, extending the whole bay. Then another thing I should point out is that these are the breakwater, which is protecting the harbor behind. And the height of the seawall typically would be 5 to 10 meters. I don't remember exactly what is the height of this particular one. And overtopping can be clearly seen here. So that gives you some estimation what is the height of this wave as they propagate into the bay. Okay, and it's quite high, 5 to 6 meters as we estimate somewhere else. And this bore actually, if I show you the whole film, will go all the way into the harbor and later on marina and flooding the land behind it. So characteristically, most of a large tsunami, large-size tsunami, 2004 and 2011 are the two more significant ones, can be characterized, the leading wave can be characterized by bore, right? And has a relatively sharp front and very long tail, very long crest, and then taper down. The damage usually caused by the tsunami are the combination of these two things, the relatively steep front and then very long crest, which provides a lot of mass of water, body of water pushing on land and carry with all the debris and the building material which would destroy by the front, right? And so that's why give us a motivation, try to understand a little better of this process. So these basically are the scope of Ignacio's study. It's a combination of laboratory experiments, numerical analysis, numerical modeling, and when it's possible, using some analytical tool solutions to help along in the analysis. So what is our goal? Basically, there are two folds. First of all, we would like to understand the correlation, the relationship between the run-up, the maximum height of the tsunami on land, the maximum vertical height called run-up, and the inundation depth at a certain location on the coast. What is the inundation depth, water depth, all right, or maximum water depth? And then also the duration is important. How long this flooding will last? And how do we correlate these important features or parameters or informations when you think about assessing the risk, assessing the flooding risk, all right, during certain given event? What's the given event? The given information, the incident tsunami information. In this simplified situation, we define the incident tsunami, which in this case is a bore height, the height of a bore, and the length of a bore, and also at the toe of a beach, all right, can be somehow approximate as a beach, and then what is the beach slope or the slope? So we would like to correlate them, getting some information on how does one depends on the other, all right? And so that's the one thing. Another thing, of course, we also like to know something about the velocity field associated with these bores. The velocity field is important is when you are interested in what is the possible forces acting on the infrastructure, such as a building, a breakwater, subject to this tsunami attack. Velocity is related to the momentum flux, and that gives you the forces. So to estimate the forces, impact forces or tsunami forces, we need to get some information, understand the information of the velocity field. So we would like to do some experiments to get those information. As I mentioned, we decided to look at this problem basically starting with the laboratory experiments, and since that's under the control, environments, we can collect some information, relevant information, to provide us some answer, understanding of the inundation depths and runoff, so on and so forth. Then also, of course, we will measure the velocity, and the velocity we're using the so-called PIV method, particle image velocimeters, and with a relatively high resolution that provides some information not only for the so-called mean velocity, ensemble average velocity field. We happen to be able to also collect some information for the turbulence distributions underneath the bore. And the type of bore we're going to look at includes the so-called undulating bore, the ones I show you on that picture, and also the breaking bore, right? The bore that breaks already before it reaches the beach. And now, as you know, in the laboratory experiments, although it's nicely controlled and simplified at the same time, but the range of parameters we can use usually are limited. In fact, sometimes it's rather limited because the size of your facility is not big enough, all right? Now, of course, there are also the issue about the scaling effect. You know, as we have the scale down from the physical, the field scale down to the laboratory scale. In some cases, you actually have some challenges to make in order to interpolate your solution properly. So the helpers for laboratory experiments actually is trying to use numerical methods, numerical models, to simulate the same process, but with a wider range of parameters, all right? And so in this case, we happen to use an open source model called SWASH, which is a so-called non-hydrostatic shallow water wave equation approach. We will come to that a little bit. I won't give you a detail, but I will say something about that later. Then, of course, when we are lazy in some sense, we don't, some of the situation that you can actually take advantage of that we can obtain some essential information based on the analytical solution methods, such as the method of characteristics, and when you have a shallow water wave type of shallow water condition, shallow water wave conditions. So combination of this and will help us to reach some kind of conclusions or informations we want. All right, so as Professor Yu says that I have been at the National University of Singapore since 2015, and when I went there, this wave tank is there already. So first thing I did, however, is to install two pieces of equipment. One is a so-called dam brake system, all right? I don't know whether you can see this or not. It's too dark. And basically, it's a gate, a gate, vertical gate, and you can lift it up very quickly by using some system here, actuator here, and you can actually control the motion if you want. But for our purpose, we simply pull this thing up as fast as possible, all right? And actually, it's a little bit dangerous. You have to control carefully, all right? And so that is so-called dam brake system. The idea is that dam brake system is that, or the terminology we say is dam brake. Maybe I think everybody knows what that means. It's that you can store the water behind this gate to a certain elevation. We call it a reservoir, or pretending that that's a reservoir. The gate pretending to be a dam. We break the dam so water gush out and form a bore in front of it. And you can play around the parameters, the elevation difference in front and behind the gate, and give you different strength of the so-called bore you can generate, all right? Then you can adjust the reservoir length. That will give you some control of the bore length, the length of the crest of the bore. Okay, that's exactly what Ignacio did for this set of experiments. Then at the same time, I actually reconstruct the wave maker. The old wave maker has a typical stroke, the distance the paddle can move. Again, it's a vertical wave maker play. Right? It's not oscillating as a linear what a hinge wave maker. It's a piston type wave maker. Just a vertical play being pushed by another actuator programmable. Then you can move at a certain speed or acceleration over a certain distance. Then that can give you a certain velocity, a certain wave system generated in the wave tank. Okay, so this is the wave maker system. Now the stroke of this wave maker is 5 meters long. So that allow you to generate relatively long wave in the laboratory setting, relatively long wave. Because the typical water depth we use is only about 40 to 50 centimeter. Okay, so 5 meters wavelength is a rather long, relatively long, long wave. Okay, so this is a sketch of the dam break system, the setup. And as I mentioned, this is the so-called reservoir. And this piece of plywood can be adjusted, location can be adjusted. So that allows you to adjust the length of the reservoir. Right? That will control the bore length generated in the system like this. Then you have the water depths in front of a gate and behind a gate, H0, H1, that can be changed. That controls the strength of the bore. Right? I will define that more clearly later on. So these are the parameter variables that he used. And anyway, so these are the numbers to vary from relatively short bore length to relatively long. The longest one is almost 18 meters long. That actually extended the whole length of a wave tank. All right. Then he measured a couple of things. He used wave gauges, measured the free surface elevation, time history of surface elevation in the constant water depth region. And also, this is a typical, the traditional, I think it's a capacitance wave gauges. Then we have ultrasonic, the acoustic wave gauges on the slope. This is a 1/10 slope. It's a glass slope, so it's very smooth surface. All right, so we're not really looking at the rough surface at all. It's a very idealized situation. It's a planar beach with one slope, and you can say that in the real situation, definitely it's not like this. You have a more rugged the terrain. Then this is just approximate situations. Then we also have another setup. That is the wave maker system. The wave maker system, the total length of this distance the bore can propagate is relatively long now. Is about 24 meters, right, from the end of motion of a wave makers. Remember, this stroke here is about 5 meters long, right? And of course, we can control it. It can stop at a different stroke, giving you different length of the bore length. All right, and of course you can accelerate the bore at a different speed, the different speed that give you different strength of the bore. So you can control those parameters to generate different kind of bore. Also, you can control the water depths. Here we simply use a 15 centimeter water depth, same beach, and for the wave maker experiments, we not only measure the free surface elevations and also the run-up inundations, but also we use PIV methods to capture the velocity distributions in the water depths in the field of view 1, and then in the vicinity of the still water shoreline. This is what we call the still water shoreline. That means the intersect between the water surface and the beach surface without the wave. Right, that's a still water shoreline. So we would like to see what kind of inundation depths can be captured and the velocity can be captured in this vicinity. Then we'll also have some independent measurements of the runoff height on this beach. Again, it's the same slope. It's a glass, smooth surface, and so one might want to do some additional experiments to look at the effects of a roughness of a beach, so on and so forth. That will open up a little bit more, give you more additional information on top of what we have observed here. All right. Okay, so if it's possible, let me see what I can do this myself here. Okay, so I'm just showing you some pictures about the dam break generator bore. It's very fast, okay? If you blink, it's going to disappear. Very simple, right? Very simple. And this is another view, and you see this breaking bore gushing out and moving toward the beach. And then, of course, what happened is that this bore will climb up the beach and breaking at the same time and reach the maximum height. I will show you some picture later on. All right, so this is a dam break system. And then here is the wave maker looking toward the wave maker down the channel. You can see the bore being generated, massive water being pushed toward the beach. And you can see in this case, basically you will see the bore front has a lot of braking, a lot of air bubble entrained, so on and so forth. And you can also notice that our tank is kind of old, maybe 30, 40-year-old. Certain parts are made of a steel plate and kind of rusty. And so it's not a perfect experiment, all right? It's not squeaky clean experiments. There's always a little uncertainties on the data, how absolutely the accuracy. Then there's certain portion, fortunately, has a glass panel, so that allow us to do some visualizations and measuring the velocity field using PIV, so on and so forth. Right? And there's a button that can be false button we can take out, and we can put a laser, generate laser sheet on the button, shooting upwards and get you the information, taking the images. Okay, so here comes on the 1/10 slope now. The first one is a long breaking bore coming in. You can see the front coming through. Then the water just keep going up, then stay there for a long time, relatively, and then go down. All right. You see the unique feature is that because the bore length is pretty long, so during certain time interval, the surface elevation is almost like quiescent, just stay there. The area remain being flooded for a long time, then the bore retreat. So tsunami is like that, okay? Because there's a huge bulk of water coming through, and so the bore front has already moved inland, maybe a kilometer upstream of the inland, but near shore, near the coastline, the water depth was still at a certain height and remain there for maybe 10, 20, 30 minutes, because the typical tsunami wave period is about 20 to 30 minutes, all right? So the water is going to flood that place is typically for a relatively long period of time. All right, so that is a long wave, a long breaking wave. Here comes the more interesting one, to me at least, is the undulating bore. You can really see the undulating bore characteristic. Here comes the first one, then there's successive oscillating bore coming through, and then they interact with the downrush flow, all right, coming from the previous undulation. I'm showing you again. Okay, these are the most interesting part of my talk. Okay, and the rest of it is going to be relatively boring. No, hopefully not. So anyway, the idea is that we're interested in looking at such a phenomenon. All right, we think we scale the problem correctly, and looking at the so-called breaking bore and also undulating bore the differentiation between them, physically, characteristically, they look different, but really the parameter-wise that depends on the so-called the bore strength. And bore strength has to be bigger than a certain number, I think 1.4 or 5. Then you will switch from undulating bore to the breaking bore. Here we go. As I mentioned before, the tsunami actually in the ocean, the real world, is very long wave, all right, very long wave. The typical tsunami could be in the order magnitude, length of a tsunami could be in the order magnitude of a 10 kilometer or even longer. A very large tsunami could be in 100 kilometers long in the ocean. It becomes smaller, a little bit smaller when they propagate into shallow water, especially in the coastal area. But still very long in terms of kilometers or tens of kilometers. And the wave height typically, even large tsunami in the ocean, deep ocean water depths typically is 3, 4, 5 kilometer. Right? The wave height is only about a meter or two. Right? So the wave height of a tsunami, or bore, if it's a bore, and compared to the water depths is very small, and compared to the length, horizontal length scale of the bore is even smaller, right? So tsunami actually is a pretty innocent type of a wave in the ocean to us, to the wave theoreticians. It's linear shallow water wave or linear long wave. Simplest kind of a wave you can get, all right? And they typically don't even break in the ocean basin. So it's a beautiful, simple wave, small amplitude wave, long wave. So the governing equation, if we look at the equation, the governing equation is really the shallow water wave equation, all right? It's even simpler than what I wrote here. This one actually has nonlinearity included in the equation. And so in the constant depths in the laboratory setting, of course, we shrink everything down to the laboratory scale, but it's still satisfying these conditions. Therefore, in the constant depth region section of laboratory experiments, the process more or less can be described by the nonlinear shallow water wave equation. Perhaps even nonlinearity is not that important for most of the cases, all right? But there are situations, especially for the breaking bore situation, when the bore strength, which is defined here, right, and is bigger than 1.5, then breaking occurs. Then nonlinearity in the vicinity of the front becomes important. You need to have some nonlinearity involved. So basically, this equation is well known to everyone here. Doesn't matter whether you study ocean wave or not in the open channel flow, you see all this equation, right? And Professor Liggis, my dear colleagues at Cornell, Professor Young's professor, advisor, and he was, no, I shouldn't say was, he is the expert in open channel flow method of characteristic. And he wrote a PhD thesis at Stanford based on this subject. And he is one of those genius type of researchers that he never stay in one topics for very long. He is a 托荒者. He is a lead front runners, right? So he worked on the open channel flow for a while and look at the method of characteristic and especially numerical methods, all right, calculating the using MOC. Then later on, he moved on to, I guess that's where Frank Young come in to look at using finite elements methods to look at the lake circulation. Again, that's a really breakthrough in some sense in our field, using the finite element methods in the fluid mechanics applied to the large lake circulation problem with the consideration of Coriolis force. All right, so that is for us is really groundbreaking at the time, and of course with the helpful hands of Frank Young, right? So anyway, he wrote a book later on in fluid mechanics, and if you're interested in, he mentioned a lot of this work he has done. Anyways, from that you can actually deduce some of the basic characteristics of these bore, this kind of bore, especially for the infinite bore, right? When the bore length is infinitely long, the relationship between these parameters, and that's well defined. These are the analytical solutions for it. So we relies on these solutions to capture some, or to make sure our laboratory experiments are being honest in the constant water depths. Or also, the other flip side is to checking how good is these kind of assumptions, all right, in our laboratory setting. So it's on both sides. We're checking, double checking on experimental data accuracies of, at the same time, see what kind of validities, whether the laboratory setting is really valid for using these kind of model equations. All right, so just keep in mind, this is nothing new here. For most of you, if you just sit down, stare at it a couple more minutes, probably recall them. Okay, so the rest of it, I'll just show you some pictures of the laboratory data, and hopefully I can give you some hints. And so this is the measurements we took at the different locations along the constant water depth region, all right? And for two different bore strengths, this is a dam break generator bore, use a dam break, and this is an undulating bore when the input, is at a generation, at a gate, the bore strength is 1.2. This is the equivalent to the flow number, basically. Right? And then this is 1.9, which is the breaking bore. And you can see the difference in characteristic. This is undulating bore, obviously. We'll call it undulating because the undulation here. And there's different colors indicating that, remember, when in the dam break experiments, we'll have a different reservoir length. All right? Using different lengths, you generate different lengths of a bore. Right? So this is a shorter reservoir length. This is a longer. This is even longer. So there's a certain time interval. You can really see a very, very flat surface. Indeed, it's like a bore. Right? And then start to decay and go down to zero. And the lower panel here is simply zoom in. This is the same experiments, and if you notice the time here is plotting from 0 to the dimensionless time to 30. So it's this corner here. When you zoom in, you can see the clear oscillatory behavior of the near the bore front. In fact, if you remember, or if you know, you probably know this already, that the undulating bore, right, if remain undulating without breaking, you can do further analysis. You will see that the bore front, the first wave, second wave, third wave, will start to separate from each other. They evolve, all right? Then gradually, each of them would evolve into single solitary wave. So this undulating bore, given the infinite distance of a channel, without friction, without energy loss, this system, this profile, will eventually evolve into a sequence of a solitary wave. All right? If the Earth is infinitely long, that's what happened to the tsunami. All right? And that will never happen because the frictional effect will damp out some energy, and of course, it's not one-dimensional in the ocean basin. So there's energy spreading, so on and so forth. Other complication will never happen. But in the laboratory, actually, numerically, you can show this very clearly. All right, on the right panel here, as I said, is for the breaking bore. And when the bore strength increases to 1.9, and then you can see the features are quite different. You still can see some undulation, could be noise, but the fact is that this front face actually is breaking, it's broken already. So visually, you will see, as a picture, I show you a video, I show you that there are air bubble and tremors and all that. Of course, when we plot this, you cannot see it. Right? And again, you still can maintain certain bore lengths, even if it's breaking. All right. Interesting enough that the bore strength is not changing. All right. That is the bore characteristic. When you solve the shallow water wave equation, you can show that. That exactly we're going to demonstrate more clearly later on. All right. Okay, so this is just another similar plot, but now I'm showing you the wave maker generate the bore. So this is in some sense to show you that using different mechanism to generate bore, as long as the parameter range is within the shallow water, within the bore range, doesn't matter what mechanism you use to generate them, they will evolve into the same thing, okay? Because the physical system, or even mathematics, you like mathematics, you will say mathematically they all satisfy the same. It's an initial boundary value problem. When you travel far away from the initial point, the source function, source term, they will evolve into the same feature, okay? So this, to a certain extent, is showing you that. So the bore strength here is 1.1, so it's an undulating bore. You have oscillation here, then the 1.6 here is for the bore, breaking bore. Again, you have this this type of a feature, and for the wavemaker generated bore, we were able to create another type of a bore, which is a decaying bore. That means at the time after for the so-called breaking bore, when the bore crest becomes 0, if you let the bore continue propagating, then the bore strength actually will decrease. Amplitude is still going to go down. Okay, so because the shallow water wave equation theory really is developed with a finite length of a bore length, right? So in some sense, in this case, you can see that this is actually decaying bore already, and the amplitude start to drop, and the bore length clearly is 0. You cannot define that very clearly. Okay, here's just a quick check, very quick check. What I'm showing here is that this is the input bore strength, okay? This is for the dam break problem. So you can measure the bore strength by measuring the velocity and water depth, so on and so forth, and you can calculate the bore input of bore strength. Then remember, we have different kind of wave gauges along the channel at a different location, and in this particular location is 2, 3. Between gauge 2 and 3, we can use the data and calculate the local strength of that bore, all right? And plotted in this figure here, if bore strength at this location is the same as a bore input bore strength, which is supposed to be, according to the method of characteristic, it should be 45 degrees, right? And then all the symbols are the actual measurements, Therefore, in some sense, give us some comfort to saying that our lab probably is not too bad, all right? And they are not scattering everywhere, and they actually agree with the MO method of characteristic result to a great extent. The R square value is 0.99, so it's really good, really close for this set of experiments. And also we get some insight or understandings that our setup really is in the shallow water wave regime, okay? So there's a double check in that sense. All right, so this is applied to different reservoir lengths as well. Each symbol here, circle, triangle, so on and so forth, represents a different, the reservoir length to water depth ratio. So doesn't matter what is the wavelength, as long as it's not 0, okay? You have a 0, that means that then you have decay bore. Then the shallow water wave equation, you have to modify. Method of characteristic, you have to recalculate it. All right. Actually, that has done before in the literature. I will show you some later. Anyway, so this is a closer F23 is a location closer to the gate than the last one. Last one is the bore strength very close to toe, actually at the toe of the beach, right? Remember, we have 1 on 10 a beach. At the toe of the beach, we'll also use the data to calculate the local bore strength. Again, compared with the incident or the initial near the gate of the dam, and again, the line is almost on the 45-degree straight line, independent of the wave of the length of the crest. Right. So as again, This is simply double-checking our laboratory setting, double-checking the accuracy of the laboratory data, making sure we understand the process better, all right? And the analytical solution provide us that confidence, all right? Okay, so for the wavemaker generated bore, is a little different in the sense that we have a stroke which is short enough so that you will generate the so-called decaying bore, all right? Now, the method of characteristic actually can work out some details used for the decaying bore, and that is represented by these lines, dashed line, solid line, so on and so forth. And then the data are represented by the symbols. And so without going into more all the details, we work out the method of characteristic solutions for the decaying bore and the non-decaying bore generated by the wave makers, and then compare with the theoretical results. The data is doesn't agree with the theory as good as the non-decaying bore with a dam break. One of the reasons could be that the dam break facility is almost in the middle of closer to the beach. All right, the distance bore travel is much shorter, almost a half, as the wavemaker generated bore. You know there's a damping effect from the sidewall, from the bottom. We estimate come to almost like 10% reduction of amplitude if you just calculate from the wavemaker all the way to the toe. All right. So there is some other processes going on that have not been considered using the method of characteristic. Also, that we have not including the estimation. We have not filtered all those factors in the laboratory data as well. Okay, so now again, this is just another checking. I'm not going to bore you with. It's similar to check the bore strength. Here instead, we'll look at the water depths. All right, this is again in the water in the constant depth region. Again, checking with method of characteristics, simply saying that they are fine. They are doing fine. Our laboratory experiments are doing fine. So this is for the decaying mode, and the formula here showing you here is simply for the non-decaying mode. So when you have decaying mode, they start to deviate from the 45 degree. All right, so move on. That's for the constant depth regions. All right, so now we're moving to the core of interest. Actually, is the flooding. It's about the inundation and the run-up. So just to define clearly what I mean, the run-up is saying that even you have a very rugged beach profile here, the tsunami coming in here is going to rush up then inland and reach the maximum highest point vertically. Right? That's what we call that vertical distance measured relative to the mean sea level, if you will, or still water level in our laboratory experiments before tsunami comes. Right? There is a still water level here, and then that's the so-called run-up high. Now, this location here is where what we call the still water shoreline. Without a wave, water is not moving, and intersecting between the still water surface and the beach profile. That's my definition of the shoreline when it's a still water. All right? And now remember, our measurement more or less for the field of view is around in this vicinity. So the water depth, inundation depth, the water depth here is measured from the free surface location to the bottom. All right, beach profile. And that is the so-called inundation depth. Later on, I will show you right at the still water location. All right, that is two parameters, physical parameter I'm going to show you. Another thing is the duration. If you still remember the video I show you for the very long quest bore, the free surface will stay almost stationary for a long time. So at a given point here, during that time periods, water depth is staying constant and for a period of time. That's our definition of the flooding period. All right, we can measure that, quantify that, and then find out what is the relationship between those three parameters: inundation periods, inundation depths, and the runoff height in terms of the input data. Right? That means in the reservoir case will be what? The strength of the bore, the length of a bore at the generation region. The wavemaker is a similar thing. All right? Okay, so again, this is a little boring, but I have to show you. But this is the inundation depth at the stillwater shoreline for the non-decaying bore for the dam break. The characteristic hasn't really changed that much. For the undulating bore, if you recall in the constant water depths, you have oscillatory behavior, undulation, then taper off with the constant water depths, then decay. Now, the only difference is that I think this is because the first wave started to break already. All right, this is in the stillwater shoreline, so the water depth there is 0 at the beginning. Right, when the bore comes in, even it's undulating bore in the constant water depth without breaking, by the time you get to that point, it's broken already. So in the constant water depth, the undulation is such that you have a bore front coming up and oscillates, right, on the more or less the same level. Here, actually, the first couple undulation has a relatively smaller, lower wave height. I think that's because the dissipation through the breaking already at that point. Okay, so on the right here is a breaking bore. Again, this front is very sharp, or relatively sharp. Of course, the scale is distorted a little bit, all right? So, but relatively sharp, there's a lot of bubbles, dissipation going on in the front, but you still can identify, in some cases, very clearly. Some of it a little bit challenging to define. How do you define the wave, the crest length, all right? But this is the features. Now, similar characteristic when you have a wavemaker generated bore, and this is the undulating bore. This is a breaking bore. One thing interesting in some of the cases, these undulation actually persists for a pretty long time throughout the entire process. All right, these are kind of high oscillations. I'm not so sure whether that's real or not. I think it's real because this is a relatively high frequency kind of oscillation. All right, there's a pretty important slides here, if I can explain to you. This is the measurement of inundation depths at the stillwater shoreline, and also runoff height measurements plotted against the the bore strength, all right, at the toe of the beach, all right, at the toe of the beach, and then it's normalized for the different. This is the dam break generated bore, so for the different reservoir length, all right. So this is reservoir length, and plotting the different symbols, circles, triangles, so on and so forth. So let's look at this simple one because kind of obvious. It's pretty all the data collapse into one curve, one trend, all right. Whatever that trend is, look like a straight line, all right. And the important message here is that it's not sensitive or doesn't depend that much on the bore or the initial reservoir length, okay? Reservoir length. And on the other hand, if you look at the inundation depth, by the way, this is the maximum inundation depth, I should say it clearly, all right? It's at that location, the surface is going to go up and down, right? And when you go up to certain location, a certain depth will stay there for a while, but you can somehow define what is the maximum inundation water depth at that particular location. So that's what we're plotting here. But this is quite different from this, all right? This is quite different from this. If you look at different symbols, that seems to me that it's depending on the reservoir length. So if the reservoir length, they all collapse into what do you call it? into one line, but start to deviate from each other depends on the reservoir length. All right, depends on wavelength. So there's an additional dependency on the wave in the Bohr length. But this length scale here, fortunately or unfortunately, or maybe it's unfortunately because I need to do something, is measured using the reservoir length. All right. So remember, the reservoir length is specifically look at certain location in the wave tank, right? So I simply install the wave gauge without even thinking about this problem. You put it down there, right? But what if I move the reservoir certain distance further away from the beach? I probably will get a slightly different kind of shape of a curve, right? Because the Bohr propagation maybe will be affected by the distance the Bohr travel, right? So ideally, what we would like to do then is to say that I want to convert this information into the information at certain location, well-defined location associated with a nearshore characteristic, which in this case simply said the toe of a beach, because you have a constant water depth, then you have a toe, you have a beach. Then the junction is the starting of this beach area or the coastal area, if you will. So defining that as the incident wave condition, incident Bohr condition. So what we like to do, this is for the duration. Again, there's some train, and there's the dependency on the reservoir length. Okay, so again, basically saying that the maximum inundation depth and the duration of flooding depends on not only the strength of the Bohr, kind of obvious, right? The stronger the Bohr is, maybe you have a higher elevation inundation, or will flood a little longer, maybe not. But also depends on the Bohr length, the reservoir length. So what we want to do, this is what I want to say, is to say that ideally, what I want to express that the inundation depth or normalized inundation depth in terms of the strength of the Bohr at the toe at the beginning of the slope, and also the slope of self. Slope definitely play a role. You can imagine that or intuitively. Then also involving the Bohr length at the toe. Okay, this is equivalent to say if you are interested in periodic wave. You're just interested in the run-up, same question, right? You want to find out the relationship between the run-up inundation depths and duration of flooding for incident periodic wave, right? So you want to specify what is your periodic wave, incident wave condition. So where's a better location to specify? You say at the toe of the beach, right? Especially in the laboratory experiments such as this, right? So, but unfortunately, what we have measured so far is the information of the reservoir length, right? So we need to convert that, right? We need to convert that. That's all I'm saying here. So we want to derive a relationship between the inundation depth, run-up, and the duration of inundation in terms of these three-dimensional parameter. There may be nothing else to talk about, to consider, but the Bohr length, LB, can be written in terms of the reservoir length and through the method of characteristics, all right? Through the method of characteristics, because we have demonstrated that method of characteristic is a good enough theory to explain the process in a constant water depth. So we simply want to find out the relationship between the gate and to the toe, or the wave maker to the toe. All right, so before I show you the final results, right, on this, is basically saying that because in the lab experiments, as I mentioned before, we have only select set of parameters to do the experiments, right? So the data, although it looks lots of them, but it's not really covering the whole range, especially the slope, right? We'll only have one slope, 1 on 10, right? So we figured that if we build another beach, we can do it, and now Ignacio will never graduate So would be also pretty tedious thing to do. And also there are better things to do than repeating that kind of experiments. And so we figure the smartest thing to do perhaps is to combine the laboratory experiments data with the numerical simulations. Maybe perhaps somebody will even say right now, smartly say, why don't you just use a numerical solution, do it directly, all right? Right? Frank Young will say it. This is all BS. Why don't you just use the Navier-Stokes equation? Okay. Okay. Now, of course, multi-purpose, right? This is an educational program, and the student need to learn multiple things, right? Understanding the laboratory skill is essential. If you just run a numerical model, garbage in, garbage out, numerical number in, numerical number out, you never get a real feeling about it. So getting your hands dirty, feet wet, actually you learn something, all right? So that's the number one. I think we actually learn a lot. Also, we measure some PIV data, so on and so forth. So that actually is one. Number two really is that we really want to know whether the laboratory data setting is consistent with the so-called shallow water wave equation regimes. Once we identify that, we're making sure we can actually use the laboratory data. That's what we did to validate the numerical result. Because in the numerical result, whether you admit it or not, there's some approximation involved. Depends on the algorithm you use. You can always show that solutions converge, so on and so forth, that you never take the asymptotic limit to zero to get an exact solution. There's always some kind of numerical error involved. Question is, what's your tolerance? And then you use laboratory. Laboratory itself has errors in there, right? Instrumentation errors, so on and so forth. So this is double checking, making sure at least in some sense scientifically they are good enough, right? Scientifically they're good enough. And so that's exactly what we did. So we use a so-called SWASH. I don't know what SWASH stands for, but was developed by a group of people in Delft Technology, University of Technology, or Technology University. Anyway, so it's based on the shallow water, nonlinear shallow water wave equation, use a multi-layer approach, so the so-called non-hydrostatic approach. And people ask you, why do you choose that? I say, because I didn't know that program very well, or algorithm very well. I want to learn something about it. If I know something, if I just run a model I know, I don't learn much at all. So actually this is a chance for my student to learn something new, not just for me, okay? So that's how we choose this model, and he did a very good job and making sure that things are checked out and cover a wide range of data parameter here. And so this is the results. I'm going to show you. Basically, is you trying to find a relationship between the physical parameter you want to look at, that include the inundation depths and runoff height and duration, flood durations. And in terms of parameters, the bore strength at the toe and the slope of the beach, and also this parameter involving both the slope and crest length, all right, as dimensional parameters. So supposedly you can run a whole bunch of numerical data, then plot this in the 4 dimension, I guess, because you have 3 parameters and some variable you want, and trying to find out what the surface represents the data behavior, right? But we'll take a little shortcut, and we are actually using multi-linear regression methods to do it and simplify the matter quite a bit. And of course, that means that it's limited to a certain extent that, for example, S cannot be very large, otherwise that cannot be correct, all right? So in fact, the data we use, we calculate the slope is only the smallest, largest slope is only 1 on 5, all right? So we never intend to have a vertical wall, right, for this case. So anyway, so this is using linear regression theory. So basically, this particular panel here showing you the formula for the inundation depth, right? Inundation depth. That is this panel here. That's this panel here. You can see that what it behaves looks like is that when the length, this parameter, is smaller than greater than a certain number, it starts become a constant, right? So if the quest length is long enough, all the data collapse into one, and they don't care about the quest length anymore. Only when the quest length is smaller than a certain number, then it behaves like a linear function, all right? So this simply represent by these, all the three equations here. If for the shorter bore, then the inundation water depth can be expressed as this kind of a linear function, linear in terms of these three parameters. And the criteria for that definition of a short or long is defined by this relationship here. Okay, this is the parameter in this coordinate system, basically carving out this line here, the change of shape there. Okay, then if a bore is long enough, then the dependency on SLB over H0 drops out. The inundation depth only depending on the bore strength and also the slope. That's all. That's what we got. Okay, based on the dam break theory. Then later on we check the theory with the wavemaker theory generated more. Now, hypotheses, walking in there, the hypothesis is that they should behave exactly the same, right? Because hopefully the wavemaker and the dam break maker board makers are both far enough, right? Far enough from the beach of toe so that the initial condition influence of the generation area has already vanished, right? So they both evolve into whatever the system allow you to have, right? And so it turned out to be more or less correct, right? Okay, so again, this is only for the dam break problem, and that is the interesting thing is that the run-up high, in fact, is independent of wave quest, to quest length. All right, the quest length is only depending on the bore strength at the toe and the slope. This is a sort of equivalent to some of the hypothesis observation we made is that for generate a tsunami shape, tsunami waves, right? The maximum run-up high really depends on waveform characteristic more than actually how long this tsunami will last, all right? And so we have done some other similar kind of analysis for using for example, the solitary wave and so on and so forth. And so next formula below here is for the duration. Again, duration also somewhat depends on the bore length, and that is showing in this figure here. All right, I should move a little faster. Okay, so this is the case that when we have using the so-called wavemaker generated wave, all right? And so look at this, probably it's a little bit easier to see for the run-up high. And this line here is really the empirical formula we find, right? Based on the dam break problem. And then we plot that the wavemaker generated bore onto the same diagram, all right? There's some more scattering, all right, effects in this case, but still pretty close enough to say that the run-up high for both decaying bore and the non-decaying bore is very weakly depending on the crest length of the bore coming in. All right? If you are brave enough to say they are not depending on it, and you can always blame us for the inaccuracy of numerical data. All right? But here is a little bit different story here. Here is considering the decaying bore, including here. And I'm not going to go into the detail, but we can actually figure out the relationships for the decaying bore for the inundation depths, and then consider the decaying bore effects in the process. Okay, because I want to just show you a little bit about the velocity profile. Now it's 11, right? I still have a little bit of time, right? Okay, if you are not sleepy, and I'm going to show you a little bit about velocity, all right? It's a little different characteristic of talk, I guess. Okay, I guess some of you probably are using PIV for measurements, so I'm not going to go into detail. Basically, it's a visualization technique, imaging analysis. You take a picture of a flow field with the aids of some seeding particles, fast speed camera, light, laser light, illumination. So now it's like not such a big deal, right? Everything can be set up relatively easy. So we have a relatively high-speed camera, so the resolution is pretty high. So we set it up. Oh, okay. So this is one point I want to make is that I make a PIV sounds like fantastic methods, but has a lot of issue here. Some of the bottleneck issue is the bubbles. When you have a breaking wave or breaking bore, such as this one, you can see the bubble entrainments from the during the breaking process going into the water, and you shine. This one doesn't even have the. I forgot whether this is a real laser sheet or not. But even say this is a laser sheet, you can see the light scattering in the highly concentrated bubble area. And here you can simply not getting any information from the images here. And for the undulating bore, there's no bubble and pretty nice. If you have the adequate kind of a particle seeding, then you can take a high-speed camera with a proper lighting, then you can get a very accurate measurements. All right, for example, here is for the constant water depth, FOV1, that's in the constant water depth region. This is the undulating bore. And what you see here is the U bar and W bar. U is horizontal velocity, W is vertical velocity, particle velocity, all right? And we put a bar here because he repeated experiments at least 10 times to get the information, necessary information for turbulence. Of course, for the undulating bore, there's no turbulence to speak of, and but he took an average anyway, and to really show that is the turbulence is very weak. So what we're showing here is the color plots for the distribution of horizontal velocity under the undulating bore, all right, the crest and the trough, so on and so forth. And this is a vertical velocity. So these then showing you the detailed profile. So under this undulating bore, basically you have a velocity going forward and backwards, all right? But there's a net velocity is going forward, right? It's a bore propagation, right? And so this is looking at a different time. If you I can walk you through one or two. So black circle, open circle is 40 to 30, all right? 38, sorry. It's very difficult to see. So so it's from 0, right? So 40 must be along the up crossing here. So the horizontal velocity is not 0, it's the net forward motion, all right? Bore is propagating forward, right? Undulating bore is fluctuating above this mean quantity, right? So anyway, so you can see the velocity moving from this point to this point, from this location to 38 is about the crest area, I think, and then moving backwards, so on and so forth. Anyway, but important feature here. I want to show you a trivial features is that velocity is almost uniform in the water column. Why? It's because this is a very long wave, right? So very long wave, the horizontal velocity is almost constant in the entire water depth. That's the first order solution at least, right? For the Boussinesq equation or shallow water wave equation. Now, another characteristic is that the vertical velocity is relatively weak or weaker than horizontal velocity, right? That's plotted over here, and also from the linear wave theory, shallow water wave theory, you can show that the vertical velocity W is a linear function in the water depth. By integrating continuity equation, I believe, right? du dx plus dw dz equals 0, then you get a linear profile for W. W is equal to 0 on the bottom and going to some large value near the surface. That deduce it, okay? Anyway, so that check out reasonably well. I believe we'll work on some theories and plot comparisons, and that is pretty good. Now, just show you some details, but I don't think I want to show you too much because we can talk about this whole day. This is the ensemble average velocity for the breaking wave, right? Now, behaves very different from the undulating bore. This is still in the constant water depth, right? So the bore is broken already. You can see that in this this is horizontal, this is vertical, and the vertical velocity in terms of order magnitude here is 1 order smaller than the horizontal velocity. It is more or less the same even for the non-breaking wave. Okay, the vertical velocity is typically weaker. Here is more dramatic, and so horizontal velocity is almost uniform. This is almost just before the wave comes, and then suddenly push it up because the bore comes, and become even bigger near the face surface, right? Because this steep front. Right, and the surface near the top move faster. Then the vertical velocity again, for the most part, is still a linear function in the entire water depth. Again, even you have a breaking or that, still not long wave. All right, so the behavior still remains more or less the same. The data, of course, become more scattering near the surface is because of breaking and the inaccuracy of our PIV data. Right, so these are all the PIV data analyzed based on PIV data. So we can go on to the later. This is later time, moving down near the back of the crest of the bore and to the tail end of the bore. And during a certain period of time, you notice that this is between minus 30 to minus 25. Minus 30 is almost here. Minus 25 is here, near the crest here. You can see that they are almost uniform in the x direction. It's like a uniform flow, right, moving toward the shore, right? And it's really amazingly close, right? And on the free surface, of course, it's a little noisy because the braking is still going on, right? But underneath it, they're almost collapsing into the uniform, homogeneous type of velocity behavior. And the vertical velocity, of course, becomes very, very, very small near the bottom when you toward the end. And again, this is simply, I don't even know how accurate these are because of noise or all that stuff, right? But anyway, this is an honest ensemble average velocity out of the PIV data. Toward the tail, so the velocity start to decrease, retreat, right? And in fact, start to reversal itself, and because of downrush, right, coming back, I guess. And vaguely, you can see the boundary layer behavior. Although we didn't pay too much attention to it, we simply take a field view, cover the entire water column. I suppose if we really want to study this carefully of a boundary layer behavior, you can actually go in there, zoom in there, and figure out the velocity. Boundary layer behavior. Again, vertical is very small and also practically the same. All right, this is toward the tail end from minus 20 all the way to 19. I jumped. Okay, I jumped quite a big distance. But as far as the vertical velocity is concerned, nothing has changed that much during this period of time. Right. All right, so the turbulence turbulence field, some of you might be more interested in it, but to be honest with you, we're still really looking into this more very carefully. Some of the conclusion, I probably cannot really make that much of a conclusion at this moment, but this is a rough distribution of the turbulence components in the horizontal direction versus the vertical direction. And again, the magnitude, you notice that is a different story now. The magnitude of horizontal velocity, this is turbulent velocity, all right? Turbulent velocity intensity. So it's U prime. U prime is you do the Reynolds decomposition. You have U equal to U mean ensemble average plus U prime. U prime, that is the turbulence fluctuation. Then we manage to take a square and do another ensemble average, take a square root of it, okay? And so the message here is that roughly speaking, you don't think about detail, just look at the roughly features that they are pretty much the same, right? The order magnitude. Remember, in ensemble average, horizontal velocity is dominating, but turbulence is different story, all right? Then this is another representation, just we're using the same data, look at it a different way. Turn it around and up and down and look at it. Trying to understand what's going on, right? So this is a vertical plane distribution, and this is simply saying that let's take the vertical water depth average all through the water depths, each cross section, right? And then blue line, I don't remember which one is which. What do you guess? I think horizontal probably is still a little bigger. Then the red one probably is the vertical velocity. Then I honestly don't remember now. Sorry for that. But they are close enough, all right? In the similar features, and they follow the same pattern. There's no obvious phase lags and so on and so forth, right? In some ways, pretty boring, but that's the way it is, right? You would like to see something spectacular happening, and then you say, wow. Yeah. Right. Anyhow, this is a turbulent profile, and then we really dive into that a little bit to look at the profile. And I'm not so sure we want to go panel by panel, but basically you can see obviously turbulence is always stronger near the surface for obvious reasons, right? And we were hoping that to see some turbulence generated by the boundary layer, so on and so forth, but relatively speaking, is really much weaker. And at this moment, whether you can say that singular point is jumping out a little bit is because the boundary layer generates turbulence or not, I don't dare to say that. But it's clear that as near the crest, remember the middle panel here represents the area that near the crest, all right? Near the bull crest. When the bull crest is arriving at that point, and then the turbulence increases quite a bit, and also the turbulence start to propagate downstream or transport down deeper into the water column, right? At the beginning, it's concentrate over here. Then you start to see the diffusion process, perhaps, or transport process at least. Shouldn't just a diffusion. There's a vacuum process going on, and pushing the turbulence from the surface downward. There's a penetration depth is changing, all right. And of course, then during the tail end of it, seem to go back to more uniform distributions in the water columns. Okay. Again, we did everything possibly we can think of, or we are capable of doing because there's some limitations on our resolution of the data prohibit us to do certain type of analysis for turbulence. But anyway, so I'm not going to go into detail. You're simply checking whether this turbulence field is within the so-called inertia range or outside, or whether there's an exchange between the boundary layer characteristic or the free surface breaking. Stay in tune. We're doing further analysis on this kind of thing. So moving to the near shore, let me use another 5 minutes. I will just conclude it. And just showing some pictures about near shore in the still water. Remember here, even for the undulating bore, it's breaking already. Okay, in the constant water depth, undulating bore is not breaking, but in the surf zone or in the swash zone, it breaks already, and so actually the behavior is such that the maximum amplitude that's more clear is much bigger at the third undulating bore. All right, third undulating bore. And that complicates the whole process a little bit, the strength of the turbulence. Sorry, this is U and W. This is still ensemble average velocity. I use a capital because on the slope, when I measure the PIV, the U is along the slope. Capital U is along the slope, so it's rotated, okay? It's a rotated coordinate system. W, capital W is normal to the beach. All right, so coordinates is being rotated a little bit. So this is not exactly horizontal velocity. It's a velocity along the beach surface. And appear to be that vertical velocity, for example, gets stronger, not stronger, that there's alternating change of directions. It's from red, first of all, then to blue. All right, so there is some kind of a complicated flow patterns happening around here. So this is again the profiles, and still in the very shallow water wave. This is even shallower. I think the behavior still persists. You have a very uniform velocity in the horizontal velocity in the water depths, and then you have more or less a linear shape of distributions for the ensemble average velocity. So I think turbulence-wise, there's only unique characteristics for this case is that at the beginning you have a very large, relatively large turbulence, all right, which is understandable. The first wave just plunge on, and then for some reason we don't know yet. The second wave actually infuse or generate certain large amount of turbulence appearing, right? And then, of course, at the end of the process, this is because of downrush, right? The water coming back and generate these turbulence. And so this is a kind of interesting. I think to complete the analysis, we actually have to go back to look at ensemble average velocity patterns. I think there's some kind of interaction between the first three waves in some sense, and to generate these kind of features. And I reserve the right to revise everything I said. Similarly, you can measure the turbulence characteristics. Now, I think instead of boring you on this, I'll just show you some of the results. Flip through it. And this is for the breaking bore. This is very interesting, very different from the undulating bore process, right? It's almost like symmetric, and have a positive on one half and a negative on the other half. It's basically uprush and downrush, all right? That kind of process. Then the vertical velocity is much smaller, at least 1 order smaller, for sure. Again, the velocity distribution in the water column is pretty uniform in the horizontal velocity directions, and then the turbulence distributions during the whole process, in this case, clearly is control dominated by both ends. One is uprush phase and downrush phase to generate these turbulence. And in this case, I can tell you blue one is definitely horizontal velocity components, and red is vertical components, right? And so there's significant difference. Okay, I'm not going to talk anymore. Conclusion. If you still remember what I said at the beginning, then I shouldn't read this, all right? But basically, we did, he did it. My student Ignacio did a very comprehensive study of the whole subject, including the measurement of the surface elevation characteristic of a breaking bore and the undulating bore. That means that the surface features and the inundation depths and also runoff height. And then he realized, he showed that the dependency of the run-up and the inundation depth and flood duration in terms of the incoming bore characteristic, namely the strength of a bore, the crest length of a bore, and also the slope. All right? And the important message here, if nothing else, is that for some reason I'm totally convinced that the runoff height, even for the real tsunami case, the runoff height is really more determined by the incoming wave shape, the front. Right? The crest length really doesn't play such an important role. Of course, in the real tsunami case, the three-dimensional geometry, bathymetry plays a role that will rule out everything I said. All right? Now, so then of course we try to understand the velocity field. I think the message there really is that shallow water wave passes through and through, and then in the turbulence, I think if we look at those data more carefully, is that there's a sign of showing is that in most areas this is like a two-dimensional turbulence field, right? It's because of the shallowness of the water depths, and also most of the turbulence, the strength more or less is pretty isotropic in some sense. Okay, so lots of information. I don't know whether you can remember anything, but hopefully you will remember some of it. But if you're not, there's articles that you can find, which is my students, part of my student thesis published in JFM not very long ago. And that's the first part of it, using the dam break problem, which establishes a relationship between the runoff height and the incident bore conditions. And the second part is the measurements of the velocity field and looking at some of the wavemaker generated data more carefully. That is still under review. Finger crossed, will be published soon. If you are interested in it, send me an email. I will send you a copy. All right. So thank you very much.
Thanks, W very much. So we got a bunch of time for further discussion. So feel free.
That means nobody understood it, or everything is well understood. So either way.
也可以啊，对啊。
可是我用中文问啊，对吗？
专有名词我听不懂，你要解释一下。
可是你有一页是讲到那个 rock up height 的那个回归的一个结果嘛？那你有提到它是跟那个就是beach toe 的那个 strength 跟那个 slope。那我想说，因为你中间好像也有做一些所谓的dimension analysis， 才会决定这两个因子来求这个 rock up height。那我想要知道就是说那个 toe strength 的这个里面到底是包含了哪些因子在里面
Translation. So what was the question was what? 他说你说最后你说是假如是什么？
老师你有提到那个 rock up height， 你有个公式去追求那个 rock up height。
对对对，就是那个刚刚那个等于看是一个经验公式 ，OK？ 你说最前面那个这个。
在前面一点。
这个。对。
所以我想要，因为我刚刚没有听得很清楚，想要知道那个F toe 的那个里面到底包含了哪些因子在里面。
哦，那个 definition of F。一开始是糟糕，对不起啊，是 U 除上 ，here we go， 就是 UB 除上 square root GH zero。H0 是它的水深 ，UB 就是说它的波的 propagation speed。 只要你这两个可以，因为水深很容易量嘛，那你只要说能够测量出它这个波到角这个海这个 beach toe 的那个时候，这个 UB， 这个是它的波 front 的 speed， 有点像 celerity 那种意思，就是讲你了解你知道说 linear wave 的话，你晓得linear small amplitude sine linear wave 你知道不知道？知道 ，OK， 所以那个 linear wave 就是说 eta 等于 a 乘上 cosine kx minus omega t， 那它这个 wave form 是 c 啊 ，c 等于 omega over k， 对不对？那类似就是这个东西，就是它这个波 front， 它的 shape 整个的 shape 移动的这个速度，假如你这个可以测量出来，刚才我给你那个 video 哈，你看看 video 里面它那个波 front 就在这样跑，对不对？那个不是 particle velocity 哦，它只是一个波形在变。假如我从这 video 一看，哦，这个波范在这跑得多快，那我假如说知道这个水深是多少，就可以说在那个附近可能那个 run up 可能是多少，就是这个道理，或者斜不一样，这 slope 到底多大？对，所以这为什么要转来转去？就是说我们刚开始做实验的时候。他给的资料是在造波的那个地点的一些资料，就是它的这个波 strength 是 input 的波 strength， 还有它的这个水槽这个 reservoir 的长度也是在这个 gate 的那个的长度，不是真正量出来的那个长度。
确认一下 ，Turbulent Profile 是都没有，就是都没有 breaking。Turbulent
Profile 都没有怎么样？
那个 breaking 就是因为你有讲一个是 breaking 的 ball， 所以它是有 breaking 的。那 Turbulent Profile 就是没有，就是没有 breaking， 就是有 wave 的，就是个 wave train 的。
Undulating ball 就是你可以想象说这个，就是这个。
对。
对，它还是有一个 ball front。
是没有 breaking。
没有什么？
没有 breaking wave， 它不是一个 breaking 的 ball。Pressure。breaking。
哦 ，breaking 啊，没有不，对 ，Undulating ball 没有 breaking， 就是这个差别就是这个在 1.25 之间，当时 1.25 跟 1.5 之间有一个 transition 这样子的话，就是这个东西一有 breaking 的话，它在 Undulation 就几乎都没有了。
你刚 show 的那些 Turbulence 的 intensity 那个都是在那个 flat channel。No，
其实我后来就有一点，也有最后几个是都在后面的，都在斜坡上面的。
那斜坡上 Undulating ball 也是没有 breaking。
哦，那个已经 breaking 了，就是它那个 Undulating ball 跟这个样子差得很远。对，在这 constant 所谓的就是在做水波的人讲 Undulating ball 的话，是这种情况，就是它第一个波比较大，然后再小，OK。然后它，假如你一直在跑的话，它这个每个 undulating 就开始分开，就 separate， 然后每个就变越来越变。其实你可以 fit 一个 solitary wave profile， 每个都可以这样。那但是到了刚才那个我讲的，事实上，到了斜坡上哈。其实这几个都破掉，已经破掉，而且它你看分布状况不太一样，到第3个波才最大了。我们现在不知道为什么，我不知道这为什么。
所以这个第3个波最大是
在这个是在 still water， 呀，还会变的，
在这个 flat，
不会，不是这样。有吗？这是往回走吧？
在这个之后。
之前还是之后？这是 constant depth。
OK。
这是没有 breaking。
那你在这个 breaking 之后的那个，这个 Shoreline 都是 interface， 就是那个前面那个。
这是自由面，对。
那 breaking 的时候你怎么去？
哈，呀，我想你的问题，
像这种类似这样。
其实它 area 的 region 可能就在这一带。 我们是 eyeballing， 没有办法。
用眼睛就是去看。
不过有的人做比较好一点，他们可能会把这一块都去掉。所以你这里面真正自由面的定义很难定义了，啊。
就是你在一个 ball， 那像你这个就是有 bubble， 就在那个区域，那大概像你这个在entrain大概多厚，就是在这个 ball 的，那这种实验里面。
再讲一遍，你说在什么在？
就是你在这个 breaking ball， 戴口罩的关系。
对对对。
就是在你这个 breaking ball 里面，就是它 breaking 之后就很多的 bubble 的这个 entrainment，那像这样子的实验，大概就也是应该是薄薄的一层而已吧，这种 entrainment 它的 depth 深度。
像这样子啊。哦，这就是我们的定义了。
对。
那样。它几乎是尽量就是说看不见的东西就拿掉，所以你看这个是不是真的自由面？但是这部分留住了，可是这边不留的话，也会它的准确度会受到这些 bubble 的影响。
对，它就是一个 two-phase flow， 但是你用 PIV 的时候，
对，
到的速度你也不确定是。
对，所以我想说，刚才我画那个 turbulent 的这个，或者甚至 ensemble average 还比较好一点了，因为所以这些东西都 ensemble average 掉了，对不对？那可是剩下来的 turbulence 里面，在这个里面准确性到哪里去就？这是说 PIV 的一个bottleneck， 就是说 PIV 假如说希望能够再发展下去的话，这个东西要解决，不能解决的话，就是这样子，再做不下，你即使做三维啊什么还是一样，那个我一个学生以前学生张广安，他们不是用 bubble， 用 trace 的 bubble， 然后来代表速度。那个讲起来有一点道理，但是也有点困难，因为就是说，它那个 bubble 第一个能够做得好的话，它的 bubble 的 density 不能够很高，也就是在这种情况之下，它的 tracing bubble 等于说个 PTV 的意思 ，particle tracing 的这种 method， 像这种情况还有可能就 trace 一下，这就没有办法，对不对？你即使用 bubble 的话，哪里 bubble 一个，当然了，它是不是用 laser 来打？它是用平常的光，不知道什么样的光打的话，不会闪这个 light scattering 不会这么严重，但是在这里面 density 还是非常大，所以 tracking 还是有很大的困难。即使你可以 track 以后，问题又是说你只是 track 的 particle 到底怎么动，跟附近的流场里面 fluid particle 水的颗粒的流动一定是不一样，但是不一样到什么程度也不能定量，不容易定量。
我想请问就是那个今天大部分这个在讨论 wave 都是 one dimension 的这种传递啊，那像地震，它从地表海洋地表这样子传递上来，这种有力轴的比较的它的传递方式。
真正你说地震造成的水波吧？
对，就是它其实从有 Z 方向嘛，从地底下这样传递上到表面，到设计这样。
对啊，对。地震所产生的海啸，当然就是跟底床的位移有关系啊。那你讲说真实的状况的话，它的地表的在地震以后忽然间的移动很复杂，对，非常复杂。它也有直向的，也有横向的，对。但是你可以想象说，假如说是横向的这个地表的位移的话，可能对自由面水面的影响不会扰动，不会是那么很大，对不对？就是你自由面在上面，我底下在横的方向这样移动，一直移动的话，只是有摩擦会产生一些影响一些水流，但是对自由面不会。你必须是垂直方向，就是 vertical 方向的位移才会自由面会有影响，对。所以真正地震开始发生的话，当然就是说假设说简单的说，它这个地表的位置只是直方向位移，就我这只手右手的话往上推一下的话，那等于说是水里面就会有反应的， 真正要做的话，那要找杨老师做 Navier-Stokes equation， 对不对？就把这个地，其实做起来对他讲很简单啊，就是 Navier-Stokes equation 啊，那就你把这个地底下的位移知道以后，就解 Navier-Stokes equation， 自由面就出来了。对，假如算得好的话就出来，可是那个算的话很慢啊。他这样算完了以后，人家都被淹死掉了，对。所以你要，假如说要做快一点的话，用什么样的近似的方式做的话，那他的做法就是说有个道理啦，就是说，因为它那个地震呢，它发生很快，对，几秒钟、几十秒钟或者1分钟、2分钟。它那个速度啊非常快，跟这个水波的传播速度比起来是快的太多太多了。也就是说，你这个地表往上一推的时候，它这个自由面的反应它的送出的波还没有出去，它位移已经停止了，啊。那再加上说这个水的压缩性很小，啊。那最简单一个假设就是说，你自由底下。用个 conservation of mass， 就是说你地底下跑出这么高，那水表就也跑出那么高，就是说地表的位移跟自由面的位移是一模一样的，就是有一个 instantaneous response。这两个这种不能成立的，这就是假如这个理论错在哪里？就是说，假如说水是可压性很大的话，啊，可压性很大的话。它自由面不会那么反应嘛，它就压缩一下就是了。那第二个就是说，假如说它这个就是产生水波可以动得很快的话，它也会说那个波会产生以后就跑掉了。所以这两个假设如果存在的话，现在我们做的方式就是说，你知道说地震以后地表大致会上升多少？老实讲了，那个 information 在当时在瞬时间也知道的准确性也不是很高，所以都是一个很这个first order 的 approximation， 对。然后呢，你就假设说它自由面的这个移动瞬间的移动也是一模一样的，然后整个问题假如是 shallow water wave equation 的话，就变成一个 initial boundary value problem， 就是在 t 等于0的时候，你自由面有一个形状，这个形状跟地表这个变形是很像或者很一样的。然后你就瞬间将让这 gravity effect takes over， 因为你把自由面推起来的话，你破坏了它的平衡啊 equilibrium， 对，那 gravity 就会把它想要拉下来，那它一拉下来有个反弹的话，就产生波了嘛，对吧？这就是海啸造成海啸最简单的解释。
谢谢。
呀。
请教一下，就是在整个问题，我想在解决问题当中有一个很重要，刚才提到就是一个 factor， 像 UB 跟 F， 跟 Flumber 都有关系。那 UB 就是产生就是这个应该是 particle 的速度嘛，所以 particle 的速度。那这一步你们忘了估计到这个通常海啸发生到 UB 这个 factor。要这个范围啊，或者影响它有没有1的实际它走的速度，这个有没有办法估计的出来？UB 跟负3的任务。
你说，我想你的意思，你是说刚才我解那个定义里面那个 UB 是吧？然后呢，你说在 Tsunami 算的时候会，
在 real case 的时候，怎么估计它的 UB 的范围？
我说，假如说一开始是多少的话，应该是可以算得出来，因为是有个 relationship。
对，这是在 hotel 后面产生以后全端的一个速度。
有一点，其实你要知道的是这个 F， 对，你要知道的是 F， 所以在这个关系里面，你必须要知道一些东西的 ，no free lunch，right？ 你一定要知道一些东西，譬如说 假如说我知道它的高度，也就是说我知道这个 HB 跟 H0，这个大概我可以估计的。我在影片里面，或者是在一些初始值的时候，也就是说一开始我刚刚不是讲说这个在深水里面啊，那个这个怎么讲，海啸的高度啊，波高大概在1米2米了不起了，那个就是这个差度 ，OK， 所以我想说，你只要知道 HB 的话，啊，那你又知道 H0 的话，H0 的话。就可以反求出 F， 那 F 的话就表示说 UB 就知道了，或者你真正要知道只是 F 而已嘛，你知道 F 就好了，啊，应该是可以求得到的，啊。OK， 对不起啊，那我就是说那个在真正海啸的时候来的时候，从影片呢或者从计算里面可以求出它的海啸的高度，这个高度就是 UB 减掉 U0。所以 UB 假如知道的话 ，U0 也知道的话，就可以求出 F。那 F 求出来就知道 capital UB。事实上，你知道F 就够了啊。
那个 F 是不是刚才你定的那个在照波的那个 impulse 你刚才说这个 F 哈。因为你不晓得这个 F， 所以是不是跟你的照波刚才有一个定义？那在哪里的 F 那个透啊 F 什么？
哦，我照波的时候啊，假如说我要知道 F， 哎，我要求这个怎么讲？
有一张影片里面有 F，
你说我照波啊？照波的话，那个 paddle 在这里，对不对？paddle 在往前面跑的话是 UB， 所以我的 paddle 的速度就是小的 UB，OK？ 那小的 UB 知道的话 ，C0 也知道嘛 ，C0 就 square root GH 嘛，就求出 F 来，对不对？
因为你那个从服务等于1一直到1.5以上哈，那中间就从duration ball 到 breaking ball。
就有一个 transition， 不是这我不忘了在 literature 里面谁定出来的，可能也就是一个就是人家过去做一些实验的什么一个 criteria， 啊。不跟我们做的结果。在这个分界还可以了，啊。
那个刘教，请问一下哈，我一个疑问哈，就是我老板pass上给我在最后1年，我老板一直希望我做 rolling wave。
哦。
就是
找刘格飞啊。
那时候刘格还。
他不是以前做 rolling wave 吗？
这个一直下来。
对。
那我不晓得你这个跟rolling wave 是不是很 similar？ 因为我看他的这个。
不是，他以前真的做 rolling wave 嘛，他是 JFN。
他做不出来，他说 Frank， you got to work out。
哦。
我说我已经毕业了 ，What's matter with you？ 所以他说，那你就回学校去帮我做一下。
嗯。
那I did do it，I have student， 黄哲伟，黄什么那个现在在一家公司，但是我都不敢发表，因为我没有把握。不晓得对不对？搞不好现在可以再发表一次，看看 test 一下。
我没有做过，不过据我了解是也是 shallow water， 对，就是 steep slope，right？ 对。
还有问题吗？
就在第一张投影片上哈，因为这个关系式里面就是 number 这个关系是红色这个第2道这个方程式里面哈，按照这样2个水深嘛哈，
这个像一个海抓降的样子，
对，几乎是
跟 HO 的关系，这样子可以搞得出来，没有问题。但是这个在定义上，在这个 definition 里面 ，H， 这 Framber 的定义是，应该是同一点的速度跟同一点的水深，所以在这边是应该是下游的水深，所以是不是那个 UB 的定义应该是在下游的地方，就是 UB 跟 HO
这两个都是 U，
对，应该是同一点的，是 UB 跟 HO 应该是同一点的，它才可能达到海抓降的一个equation， 因为这个是海抓降的是 Y2 跟 Y1 前后的水深的关系，前后水深关系的 Framber 是同一点的，下游的水深。下游水深，就是 UB， 是不是那个I know， 那个大写的 UB 是下游的，好，这样我看懂了，我大概了解了。我刚刚有一点就是小写的 UB 是上游的，大写的 UB 那个 Framber 你写那个 UB 是应该是下游的水深，那这样没有错 ，OK。你两个式子一个大写的 UB， 一个小写的 UB，
对，
我搞错了那个大写的 UB 是应该是下游的，这是downstream 的下游，就是在 bore front，
不就是
前面一点是大写的 UB，
事实上的 bore front 是这样子。
对，大写的 UB 是同一点，没有问题，我自己弄错了大写小写的问题，好，谢谢你。
还有问题要请教刘老师吗？我是。
老师好，我想问一下那个实验配置的那个地方，在那个岸的部分是用玻璃板当做那个斜坡嘛？那这个选择有什么原因吗？还有那个玻璃板的下面好像有一个 sensor。它测量的时候是不是会受到那个玻璃板光折射还是光的交影影响？有考虑这个？
你说哪里啊？
那个实验配置的那个地方。
我做实验啊。这过去了。
应该蛮前面的。
等一下，就可以，这个可以看得到吗？
对。
还是再前面一点。
前面有更前面有一张图，不过刚刚那张应该是就可以。
这个。这样。
所以选在斜坡那个地方是用玻璃板的，对。
这个地方。
对，那一块是玻璃板。
这一块是玻璃板，对。
对，那选择这个玻璃板是有什么原因？
是因为我们要把这个光线从底下打上去，因为一般的有两种选择嘛，你可以把 laser 从上面打的话，那有波的话就比较讨厌，因为光会被这个波的运动，这个反射啊、折射啊，所以它的光不会很均匀，所以量起来的话，要怎么样做一个分析，就要再多做一些手脚，然后那个手脚有时候也不见得做得很准。
对，所以我第二个问题就是说，它既然是玻璃板，它就应该有光折射的问题。
也有了，这你假设真的这样的话，最好就像这种光线，就是说是平的，直的这样打上来。但是你即使说是玻璃的话，也讲的话还是有点折射嘛，对吧？
对，而且它是反斜的。而且它是反斜的。
反什么？
斜的
斜
你说这个对，当说最理想的话，这个东西你把这样tilt的这样打上去也比较好一点。
那个阳光雷射其实打过那个玻璃面的时候，其实它的强度很强，基本上它不会折射下来，它就直接传过去，然后打出来是一个线，对，应该不会有这个。
好，谢谢老师。大家还有其他问题吗？这样子时间的关系，我们演讲就在这边结束。那如果后续有什么问题的话，刚刚刘老师有deliver 他的那个 content information，大家可以再 跟他联络。那我们再一次鼓掌，谢谢刘老师。